Okay, if you're just here, you missed the first part. It was like 42 minutes of equations. But what I want to do is build a Python model of a double pendulum. And so in the previous video, and I'll link down below, it's also part of this playlist, I derive the differential equations of motion for a double pendulum. And so a double pendulum is two masses on strings. You can't really do it this way because it actually wouldn't stay in two dimensions. But anyway, mass M1, M2, and it's essentially a pendulum on the end of a pendulum. Now, if you missed it, last time on this episode, this is what I got to. Right there. So these are my two differential equations of motion. And what I want to do is to model this if I know the initial conditions. So what I need is an expression for theta 1 double dot and another expression for theta 2 double dot. But you can see here that these two equations have both terms, both theta 1 double dot and theta 2 double dot, theta 2 double dot, theta 1 double dot. So I have two equations to unknowns. I need to solve these two equations to unknowns. Now, I think I can do this. I think I can do this by just saying a whole bunch of this stuff is assigning it as a variable and then solving it. I've done this more than one time and I made a mistake. So there's a good chance I'm going to make a mistake. And if we make a mistake, we make a mistake. Okay, but so what I want to do is to rewrite this equation. I'm going to call this term A, even though A is not constant. So I'll need to recalculate that every time. And this will be B theta 1 double dot, C theta 2 double dot, and then I can just call that even a constant. So I have a whole bunch of constants, right? Actually, I can even combine these two together. Yeah, let's do that. Okay, so let's start off and writing down my constants, and then I'll rewrite these two equations, and then I'll solve two equations to unknowns. And then it's okay that we don't have to put it all together because we can put it all together in Python. That's what's great about Python. Okay, so I'm going to write down these constants. Here's my starting page that I do like this. I use the wider paper. But this is whiter, and so it looks brighter over here. It doesn't look kind of like yellowy, but whatever. Okay, so I'm going to first say this. A equals negative M1 plus M2 G R1 sine theta 1 minus M2 R1 R2 theta 2 dot squared sine theta 1 minus theta 2. Now, that is not a constant term. That's fine. It's not a constant. But it doesn't have theta 2 dot in it either. Okay. And then I'm going to say B is equal to M1 plus M2 R1 squared. And C is equal to M2 R1, R2, not that, cosine theta 1 minus theta 2. So with that, my first differential equation looks like this. A equals B theta 1 double dot plus C theta 2 double dot. See, isn't that nice? That's a nicer equation. Okay, now I need to do that for the second equation. So let's see, A, B, C, D. Should I use D? I don't want to use D. I don't want to use E. So let's go to F. So let's say this is a box. I put box around good stuff. F is equal to, okay, I'm going to get all the non-theta 2 terms, the double dot terms. So it's going to be negative M2 G R2 sine theta 2 plus M2 R1, R2, theta 1 dot squared sine theta 1 minus theta 2. And it's close to this, and I actually can make a different variable. I'm just going to, I don't really even care. And then I'm going to get M2 R2 squared. I don't have that one already. So let's say A, B, C, D, E, F, G, not G, A, B, C, F, G, H, I, no, H. Let's do K. K is M2 R2 squared, and then I have another term. I'm trying to think of a good variable. A, B, C, D, F, G, I, J, K. LMNOPQRSSTUV. Let's do W. W is equal to M2 R1 R2 cosine theta 1 minus theta 2. And so with that, I get the second equation is going to be equal to F is equal to M2 R2, that's K theta 2 double dot plus W theta 1 double dot. Box it. See, those are, I can solve those two equations, right? Okay, let's just go up here and solve this one for theta 1 double dot. So if I subtract that from both sides, divide by b, I can do that in one fell swoop. Theta 1 double dot is going to be equal to a minus c theta 2 double dot divided by b. I'm trying to think. Should I write that as a over b minus c over b theta 2 double dot maybe? Okay, so now I can plug this term in down here, and I'm going to get F equals K theta 2 double dot plus W times this. So that's going to be plus AW over B minus CW over B theta 2 double dot. Now I can factor out the theta 2 double dot, and I get, I want to do this all in one fell swoop. Let's do it. So let's get theta 2 double dot is going to be equal to, oh, I shouldn't do that. That's a bad idea. Okay, so let's say F equals K minus CW over B theta 2 double dot. And then let's add this, subtract this term from the other side. So I get minus AW over B plus. I know that's messy, so let's get a new piece of paper. Okay, so now I have, this is right that, F minus AW over B equals K minus CW over B theta 2 double dot. So if I solve that for theta 2 double dot is going to be equal to 1 over K minus CW over B times F minus AW over B. And then let's rewrite theta 1. Theta 1 double dot is going to be equal to A over B minus C over B theta 2 double dot. So I got it. I mean, it looks dumb, right? But if I make all those constants and I recalculate them all the time, I can get theta 1 2 dot and theta 2 double dot. And why do I care? Okay, so this is what we're going to do. We're going to use the Euler method of a numerical calculation. So what I'm going to do is to break the motion into small time steps, delta t. During each of those time steps, I can define theta 2 double dot as the following. I can say theta 2 double dot is going to be equal to the change in theta 2 dot with respect to t. And so if I assume this is constant over that time interval, which it totally is not, but if I assume that with a small enough time interval, it's close to being true. Then I could write this as theta 2 dot minus theta 2 1 dot over delta t, where this is the theta 2 dot at the end of the time interval, this is at the beginning of the time interval, and I can use this to solve for theta 2 dot at the end of the time interval, theta 2 double dot, by multiplying by delta t and adding that, and I get theta 2 dot equals theta 2 1 dot plus theta 2 double dot delta t. This is the Euler method for numerical calculations. This says that if I know the initial angular velocity and I calculate the angular acceleration, which I can do up here, and multiply by delta t, I can find the new angular velocity. So this is the velocity, angular velocity update equation. And it's just mostly true. I mean, it's not exactly true. But now if I go on and I'm still looking at theta 2, if I do this, theta 2 dot is equal to the delta theta 2 over delta t. That's going to be theta 2, 2 minus theta 2, 1 over delta t. Multiply both sides by delta t, and I get theta 2, 2 equals theta 2, 1 plus theta 2, 2 dot delta t. Okay, so now I just did the same thing, but what I did change is, since I just calculated the new angular velocity, I'm going to use the angular velocity at the end of the time interval, not at the beginning. And yes, there are better methods that you could do here. You could do better numerical models to do this, but I'm going to use this one. Now if I repeat the same thing for theta 1, I get theta 1 dot 2 equals theta 1 dot 1 plus theta 1 double dot delta t, and theta 1, 2 equals theta 1, 2 plus theta 1, 2 dot delta t, and then t2 equals t1 plus delta t. So that's it. That's my numerical model. So I'm going to start up here. All these parameters change each loop, right? So I'm going to break this into small time steps, and during each of those time steps, I'm going to first calculate all these constants. Next, I'm going to calculate theta 2 double dot, then I'm going to calculate theta 1 double dot, and then I'm going to use that to update theta 2 dot, update theta 1 dot, update theta 2, update theta 1. Yeah. And then do it all again, as long as I want. And I guess we should get started. Okay, so I'm going to do this in WebVPython. It's now called WebVPython. There are a lot of features in there, like what we're really going to use is a sphere and a cylinder. But, you could just model this straight out without having to make a 3D animation. I like 3D animation, so that's what I'm going to do. I'll try to include a tutorial link down below for how to make all these objects. If you don't see what I'm doing, then look at that video. I don't want to have to spend too much time doing that. Okay, so let's just draw some things. Let's draw the double pendulum. Now, I am going to have to remember that in order to draw things in GlowScript I need to give it an XYZ coordinate. So I'm going to have to switch back to my XYZ coordinates in this case, which I need to find that piece of paper just so I can have it down, but that's fine. Okay, so let's just jump over here to WebVPython. Hello, WebVPython. This is actually trinket.io. It's a slightly different version. I am going to give you the link to this down below, the link to this code. You can edit it without even having to log in. That's what I like about it. So let's just get started. The first thing I can do is to pick some constants, right? So g equals 9.8. I'm using the scalar version of g. I'm not using the vector version. Now I need m1 and m2. I'm going to pick them the same, but we can have them different. Let's just say I'm going to call capital M1 equals 0.1. It's 100 grams. That's fine. M2 equals 0.1. And then the length of the two strings, R1 equals, I feel like 0.1, right? 10 centimeters. So 0.1, R2 equals 0.1. Now, and I'm using R1 and R2 because when I derive these things, I didn't want to use L because L is a Lagrangian. I didn't want to use lowercase l because lowercase l looks like a 1. I don't like it. There, I've said it. Okay, so let's just start and draw this whole thing. Oh, now I do need also the initial angles and the initial angular velocity. So I'm going to start with both the angular velocity 0 and the angles I'll just pick. So let's say theta 1 is equal to, I'm going to say 35 degrees. I like to think in radians and degrees. 35 times pi divided by 180. There is a better way to do radians, but I like it this way. Theta 1 dot, that's the angular velocity. I'm going to set that equal to 0. Theta 2 equals, let's do 55 times pi divided by 180. And theta 2 dot equals 0. So the first thing I'm going to do is put a little pivot point. I can have a little sphere that I can attach to. And it's not super important, but that way I don't have to have everything attached to the origin. So let's say I'm going to call it pivot. And it's an object type of sphere. its position, I'm going to move it up R1. Why? I don't know why. So that's going to be vector 0, R1, 0. The radius is going to be equal to R1 divided by 20. I don't know why. Okay, so now I can put mass 1. I'm going to call mass 1 an object. I'm going to use M1, which is probably a bad idea. But I'm going to do it anyway. Okay, so lowercase m1, it's going to be a sphere. Now, here I do need to go back to my equations. Let me pull my paper. See, here's my notes from the last time. I can use this. See this x1, y1 stuff right there. I'm going to use that. So let me put this right here so I can see it. Okay, so let's just, I can do it all in one fell swoop. Okay, so the position is going to be equal to, this is mass 1, is going to be equal to, let's put it right here, equals vector r1 times sine theta 1, and the y coordinate is going to be negative r1 times cosine theta 1, 0. Okay, but I want to put that below the pivot point. So I'm actually going to say this is pivot.pos minus this. Pivot.pos is the vector location of the pivot. Yeah, so I think that'll work. And then I need to give this a radius. Let's say radius equals, well, I want a little bit bigger. So let's say R1 divided by 10. And let's make it yellow. Color equals color.yellow. I shouldn't have this such a long line. And that's that. Okay, let's run this and see what happens. There. Oh. Minus. Plus. I guess it should be plus. This should be plus. Yeah. Okay, so there's my pivot and there's mass 1. I'm pretty happy. Okay, now let's make mass 2. Let's actually just copy this whole thing. Okay, M2, let's just copy it and change everything. Okay, so M2 is going to be equal to sphere, pivot. Now I have to do, this is going to be equal to, actually I can do a little trick here, right? I already know M1's position. So I can just say plus M1.pos plus, now I can just change this to R2, theta 2. Okay, now this one also I'm going to add on here after the color. I'm going to say make trail equals true. Okay, when it moves, it'll make a trail. And there's an error. No, it's not. Where's my other ball? Oh, there it is. Okay, that's it. There's my two masses. Next thing I need to do, just graphically, why does that not show up? I guess because I have this. There it is. That's fine. I want to make the two strings. So let's call this S1 is going to be the string from the pivot to mass 1. So it's going to be equal to a cylinder. The position is going to be equal to pivot.pos. So in Python, a cylinder has two important things. The position is the location of one end of the cylinder, and axis is a vector from that end to the other end. So the axis is going to be equal to, let's just do it all one type. Axis is going to be the vector, which is mass1.pos minus pivot. So it's mass1.pos minus pivot.pos. Now the radius is going to be equal to, let's say, R1 divided by 20. And let's leave it as gray. And nothing happened. POS must be a vector. POS. What happened? Cylinder equals POS dot pivot. Pivot dot POS. Oh, that's right. Okay. Oh. Radius. Oh, ha. Radius. It made a radius of 1. Okay, that's a little bit big. Let's make this 30. And that's just aesthetics. It doesn't really matter. Okay, so that's that one. Now I need the other string. Let's just copy this. So it's going to be S2. Its location is going to be mass1.pos. And then the axis is going to be mass2.pos minus mass1.pos. And then other than that, it should be good. Yeah. Okay. So we have that. And now we just need to start animating stuff. Maybe I should save this. Double pendulum new try. I have multiple of these. That's why I'm saying that. I like the double windows, but okay, that's fine. So now the next thing I need to do is I need a time. I need a dt. And one of the things is I'm going to make it kind of small because there's a lot of calculations going on here, a lot of approximations. This is not the best method to solve this particular problem, but you can fix bad technique with a small time interval. So there's that. Okay. So I have the initial conditions, theta 1, theta 2 dot, theta 1, theta 2. I do need to, let's go ahead and make the loop. Oops, I knocked over my light. Okay, so I'm going to say while t is less than 4, rate 10,000. Yep. So rate tells Python don't do more than 10,000 steps per second. And since I have a time step of 1/10,000, this will make it run in real time. Now, the thing I always forget is t equals t plus dt. If you don't have that, you'll have an infinite loop. You'll never get to t greater than 4, and it'll go on forever. And I always hate making that mistake. Okay, so the first thing I'm going to do, every time I get the loop, the first thing I'm going to do is to calculate these coefficients. Oops, I dropped something else. So I'm looking at my sheet right here. I'm going to type these up. So I'm going to say a equals negative m1 plus m2 times g times r1 times sine theta 1 minus m2 times r1 times r2 times theta 2 dot squared times sine theta, sine theta 1 minus theta 2. That's A. Just like I said. Okay. Now I need to calculate B. B equals M1. And notice I'm using the capital M1 and M2, so I don't have to type M1.mass or anything like that. I'm just using, and that's not the best. I should have really do M1.mass, but I didn't do it. And, what are you going to do about it? What are you going to do about it, huh? Times R1 squared. Also, I should point out this. I always get scared doing this. I want to make sure it's not theta 2 dot squared to raise to this whole power, but it does work that way, so it's fine. C equals, and I'm using lowercase, M2 for the variables, M2 times R1 times R2 times cosine theta 1 minus theta 2. F equals negative M2 times G times R2. I'm going to make a mistake here. I know it. Where am I? M2G R2 times sine of theta 2 plus M2 times R1 times R2 times theta 1 dot squared times sine theta 1 minus theta 2. And again, these constants, whenever I change my values, these constants change too. And that's what I want. Oops, didn't move that down. Okay, K equals M2 times R2 squared. And finally, W equals M2 times R1 times R2 times cosine theta 1 minus theta 2. So I have all my constants. Now, where'd I go for the other one? Here it is. There it is. Now I'm just entering these equations. right here. Those. Okay. So I'm going to call, oops, that's bad. So I need to calculate theta 2 double dot. So I'm going to call it theta 2 d dot, right, for double dot. I know that looks like theta 2 dot with extra d, but you know what? I don't want to type out double. That's too much work for me, and I don't want to do it. Okay, so it's going to be equal to f minus a times w divided by b, all of that divided by k minus c times w divided by b. And then I can calculate theta 1 dot. Theta 1 double dot, is going to be equal to a divided by b minus c times theta 2 double dot divided by b. Hope this works. Okay. Now, I have theta 1 dot and theta 2 double dots. I can use that to update theta 2 dot and theta 1 dot. So I'm going to do that. And I don't have any comments in here, and I apologize. You can go back and make comments. I'm just trying to get it to work. Okay, theta 2 dot equals theta 2 dot plus theta 2 double dot times dt. Now, this is something, if you haven't done numerical calculations before, this is important. Notice I do not have the indices theta 2 dot equals theta 2 1 dot because I have the same variable on both sides. This is a make equal to sign. This says take the value of theta 2 dot, add this theta 2 double dot times dt, and then make that the new variable. So I don't have to worry about all those indices and everything like that. It just makes it a lot easier. Okay. Theta 1 dot equals theta 1 dot. There's so much stuff here. If this runs the first time, I don't know what I'm gonna do. Plus theta 1 double dot times dt. Now I can use the theta 1 dot and theta 2 dot to update theta 1 and theta 2. Theta 1 equals theta 1. I did 2 first, but it doesn't matter. Theta 1 dot times dt. Theta 2 equals theta 2 plus theta 2 dot times dt. I've already updated time. Right down there. I don't know why I got so... Okay, so that's it. But now what I need to do is to update all the animations. So the first thing I need to do is to move mass 1. It has a new theta, so it has a new position. So I'm going to say m1.pos equals pivot.pos plus vector. I'm just retyping what I had before. R1 times sine theta 1 negative R1 times cosine theta 1, 0. That's all I did, right? But since theta 1 changed, then the position changes. Now let's update mass 2. M2 equals m2.pos equals, this is going to be equal to, yeah, I guess it'd still be pivot.pos. Pivot.pos plus m1.pos plus vector r2 times sine theta 2 minus r2 times cosine theta 2, 0. Now I need to move string 1. So I need to move its position. I don't need to move its position. Its position is always going to stay at that pivot, which doesn't change. I just need the new axis. So I'm just going to retype that. S1.axis equals m1.pos minus pivot.pos. Now string 2 I do need to move. S2.pos equals m1.pos. And then I need to do the new axis. S2.axis equals, okay, it's going to be m2.pos minus m1.pos. I think this should work. I mean, I think I have everything there. Okay, I'm going to save it. I don't have super high expectations. I don't know why. I know you should trust yourself, but this is only running for 4 seconds, so let's go. Something's not right. Okay. I think this is wrong. Mass 1 should be just, I don't think I add, yeah, I did this, I was thinking about this. Take out this pivot, and then down here, do that again. I'll just need to add it from mass 1. I don't need to add pivot in there twice. Oh, something got mad. What did I do wrong? Okay, let's see. Just comment out all the stuff and rerun it. Let's see if I can do that. Oh, there it goes. Okay. I think that's okay. I think that's okay. Well, I don't know why it took so long to run. Let's see. Let's try a bigger angle, because that's not chaotic. Theta 2 is, let's say, 75. Why is it taking so long to run? I don't know. It kind of scares me. I think that's right, which is a double high five for me. Okay. What I think doesn't matter. What I can show matters. So I have one more step. And this is almost as long as the last video, so yay. If this is legitimate, then the total energy should be constant. The pivot point up here does exert a force on the system of the two masses, but it doesn't do any work, so it doesn't move. So if I plot kinetic plus potential equals the total energy, that should be a constant thing. So let's make a graph of the potential as a function, the energy. So I'm going to go up here and say, let's make a graph. So G1 equals graph, title equals double pendulum. I don't know why it's like put a title. Double pendulum. It's a weird word. X title equals time. This is plot versus time. And then Y title is going to be equal to energy in joules. And then I'm going to have three graphs. I'm going to have FE equals G curve, color equals color dot blue, label equals total. I'll put total E. And then I'm going to say FK equals G curve, color equals color dot red, label equals K. And then FU equals G curve, color equals color dot green dot, label equals U. Now, I need to calculate the kinetic and the potential energy, and I have theta dots and thetas, right? So in order to, I need to have the value of x dot and y dot for both the terms, and also x and y, which that's, I mean, just y. I only need y because y comes in the potential energy. So I'm going to look over here in my old notes. Good thing I saved this, and I assume it's correct. Actually, I can do this. T. Where's my T? There's X. T2. Why? Here I have T1 and T2. I'm missing a page. Yeah. Missing a page. I don't have to calculate that because, yeah, I have here, I have the Lagrangian. I already calculated Lagrangian. So that first term on there, that is my kinetic energy term. It's already in terms of theta 1 and theta 2 dots. So let's just type that out and see if we can get this to work. Oh, I'm covering up my stuff. Okay. So down here, I'm going to say, let's just put it at the end. It should technically be before the time, but I don't care. Make this bigger. Okay, so I'm going to say t equals 0.5 times, I'm just typing in my equation here, 0.5 times m1 times r1 squared times theta 1 dot squared. So it's just going to be times theta 1 dot squared plus, I can't see that like that, plus 0.5 times m2 times r times parentheses r2 squared times theta 2 dot squared plus 2 times r1 times r2 times theta 1 dot times theta 2 dot times cosine theta 1 minus theta 2, that's it, plus r1 squared theta 1 dot squared. And that's my kinetic energy. I hope. I think it is. Okay, now the potential, in my Lagrangian I have minus u, so I just need to multiply these potential terms by minus sign. Again, if this works, I'm going to be so excited. So it's going to be equal to minus m1 times g times r1 times cosine theta 1 minus, oh, here, I'm going to write my other version. I'm going to write like this. Minus m1 plus m2 times g times r1 times cosine theta 1 minus m2 times g times r2 times cosine theta 2. And then that's fine. Okay, so now I have kinetic energy and I have potential energy. I can plot those. So let's say Fe dot plot, it's going to be T, and the total energy, which is going to be T plus U. Fk dot plot is T and T. I guess it's okay. And then Fu dot plot is going to be T and U. So what do you think? Think it's going to work? Save it. I'm a little scared, to tell you the truth. I mean, it looks fine, and I've had this look fine where the energy was not conserved, and I've had it where the energy was conserved, so. And I have an error. Fu equals G curve, color equals color, label equals, oh, label equals U. I can fix that. Label equals. That was easy. Okay, it's running. There's, oh. I'm kind of happy. Can you tell? So there's your total energy. The kinetic energy changes, the potential energy changes, but the total is constant. So, I mean, it doesn't mean that it's right, but if this was wrong, that would mean that it's wrong. Okay, so modeling the double pendulum. Let's just go wild, right? Let's do one while we're here. Let's just celebrate. Let's change theta 1 to 81. That looks nice. Chaotic. Excellent. Energy still conserved. I mean, oh, and this is 3D, right? So you can rotate that around if you want to. Okay, so I'm going to put the link for the previous video where I derived this stuff down below. I'm going to put a link to this code down below. Now, there is another way to solve this. And then I want to do that, and then I want to maybe use this to make show chaos. But I'm definitely going to do another method that does not use Lagrangian, and it's a little bit easier to code, but it's not quite the same thing. And I may wait a while to do that. But these two go together, and they're going to be in the playlist. I'm going to put the links together, and hope you enjoy that. And it's shorter than my previous videos, so there you go. Okay, so you definitely should play with the code. That's how you learn stuff. If you make mistakes, it's cool too. Okay, I'm done.